Hello and welcome back to Project Euler series. It's been a while since the last time we had some episode. Since then, I've solved some problems, mainly with bigger indices. But among the first 100 of the problems, we had like 60, and that was almost 2 years ago, which is funny. So we have to firstly we have to remember what we did, and we need to continue for a little bit. So firstly I will open my account, Project Euler, if it wishes to open. Yes, it wishes to open. So here it is, and now we want to solve problems from archives. I've made some posts. No? I guess not here. For easier problems, they are already comprehensively explained in these posts, I guess. So let's go for the next problem, which is 61st problem. Cyclical figurative figurate numbers. So we know that there are some numbers of some shapes. We definitely know a lot about square numbers and triangular numbers, but apparently there are more types of numbers: pentagonal, hexagonal, and so on. So there are some definite formulas for them, formulae. And then they say to us that they consider this ordered set, and they find some interesting properties. So first of all, it is cyclic. So we can take the string of digits 812882, and if we consider the cyclic string, then these these three 4-digit numbers are just some substrings of length 4 of this string. Also, each polygonal type is represented by a different number in the set. This is the only set of 4-digit numbers with this property. So we want to find the sum of the only ordered set of 6 cyclic 4-digit numbers for which each polygonal type, triangle, square, pentagonal, hexagonal, heptagonal, and octagonal, is represented by a different number in the set. Well, it's interesting. So how would we like to write that? Well, so do they need to be in this exact order? So they say that it is ordered set. Why? It should be exactly ordered set and not just any set. They don't say that we definitely have to have a square after the triangle number and pentagonal after the square number and so on. So they can be in any order. Well, that is interesting. That is definitely interesting. So how can we approach this problem? So first of all, since it's about 4-digit numbers, I don't see any reason to write some arbitrary precision arithmetic for this problem. Let's just solve it. Basically the exact problem, they write it down here. So we create problem. I forgot what I have in these files, so I'll create new one just from scratch. So prob 0061.cpp. Why 2 times had executable? What? Ah. What the hell? No. Oh, it doesn't understand what I want from it. Okay. And let's switch to this one. So, how do we solve it? First of all, we need to write some auxiliary functions, which we'll need later. The first one of them will be like main function. So let's speed up the input. And we want to we want to solve tests. Also, I'll write some very strange auxiliary class, which will be called timer. You will see why I want to do it a little bit later. So, timer of, let us put it this way, chronon high resolution clock time point. So it will say that it starts some timer at the moment of this time point. Let me teleport myself here. Okay. So we create a timer, and its start field will be exactly this type. Okay. I don't know, let's also write using clock equals this. So it will be easier for us to change it if we want it later. Okay, it's a timer. And I also want a comment. Let's call it prefix. And prefix will be moved. You'll see where I'm going with it. So prefix will be moved from prefix, so I don't need const and the reference. And when we want to destruct the timer, we will do the following. We will print in stdcr std format of some information. We don't have format here. 23rd. Cost 23rd. So here we write that this and this. So we want to write the prefix. Then we want to write the pretty duration of the time that has elapsed, and we want to print this. So as for the duration, we will store it in a separate variable, which will be of type duration, and it is equal to this minus a start. And also I'd like to, I'm not sure actually how C++ works in this situation, but I'd like to put this, I'd like to make this argument optional. So if we don't write anything, that it starts at this moment. And we define it as timer with prefix total time elapsed. So it will be the first object that is created during this execution of this program. It will store the start variable, and then at the end of the program it is destroyed, and we see how much time it took to work out. For that to work, we also need to define pretty duration, which we will write now. So let's say pretty duration clock duration dur, and that should be easy. So we definitely don't want to work with anything greater than how do I want to do it? Well, basically, if duration is less than 1 microsecond, how can I define your you see it's in nanoseconds always. It's strange actually. How can I be sure that it is in nanoseconds? Nanoseconds of what? And I want to write how many of them. 1000. Let's just define some constants. So if the first constant is microsecond, which is equal to 1000 nanoseconds, then there is a millisecond, which is 1 million. Then there is 1 billion. Then probably let's also write minimum, not minimum, 1 minute. And probably 1 hour. Although this shouldn't happen at all. Okay, so what do we do then? So if it is less than 1000 nanoseconds, let's return something like stuff like this. So several nanoseconds. And here we write something along the lines of semicolon. Oh, just colon. Just like this, I think, yeah. And we divide duration by nanosecond. We also want nanoseconds 1. We divide it by nanosecond. Else, so nanoseconds is over. Now we want to compare with millisecond. So if duration is less than millisecond, then we want to write it in terms of nanoseconds, microseconds. And here we already want to... Well, actually, I want to divide it in by floating point nanoseconds. And it is... You see, it's duration of long and nano. And I want to have double and nano. Right? Can I have it? It should be steady clock. I cannot have it. Okay. But can I at least have this? Why? Why? What? Now it works, but all other don't work. Okay, let's replace it. Okay. So we write it in microseconds, but this time we kind of want to only write 4 digits, probably. And then if it's less than 1 second, we write it in in milliseconds. So now if it is less than a minute, then we write it in seconds. If it is less than an hour, then it's tricky because we want to write separately several minutes and separately several seconds. Yeah, I want separately to write separately several minutes and several seconds. Well, I think we can do it this way. So first of all, let's calculate the total number of minutes. And we do this let's call it total minutes equal to floor of duration divided by minutes. And then we want to subtract it from the duration. Okay, it makes sense. And we want to return something like this. So we will write, so if total minutes is less than 60, then we return this colon and then several seconds. And this number should be something like exactly 2 digits before the decimal point, and then exactly 3 digits after the decimal point. So for that, I'd like to have double residual seconds double equal to the following thing. So we take residual seconds, we divide them by seconds. So now it is something between 0 and 60 exclusive. Now we want to multiply it by 1000. Now it is strictly less than 60,000. Now we want to take to round it. And then I want to take the minimum of size t of this number and this round. And then I multiply it back by 1000. So this is what makes sense to me, and we just write it here. Does it work? Is it legit? Can I write? Ah, okay, this works, right? And also, I also want to have it here. Can I just write 2? I don't know. Probably yes. Else, we also add total hours, which is this divided by 60 and this percent 60. So this is some sort of pretty duration. That makes sense. And this will be working in this timer thing. Now, when we write solve tests, also I'd like to free open a little bit. I want to free open txt. Let's also make some definition. Define probe 0061. Then here we have txt slash probe dot input this dot txt. and std out. The same way, but w, and here we have output, right? All right. Okay, and then we solve tests, and here I'd say that we do something like this. So we go for size ti from 1 to I, and we go okay, let's also do something funny. Let's also make bool active equals true, and let's write the function deactivate. And here, only if active, then we print anything at all. Okay, this is lovely. And here we say that if we fail to solve test of I, so first of all, we create a timer. Case timer of which says like test case this. And if we fail to solve this test, then we deactivate the timer and break. Finally, we want to write the function bool solve test. And we will not use test index post probably. The next thing is will be the structure instance. And in our case, what is the instance in this problem? So in this problem, the instance is simply the number of forms, polygonal types. I guess that's it. Just it's always 4. Well, we may say that it's always half the number. We can probably say that it's always half the number. Well, you know what? Let's say that one of the parameters is the length of the number, and also one of the parameters is how much do we step each time. I think that will be nice. So instance is length. Also the instance is jump. And also the instance is the vector of shapes. Now let's write a function that reads this instance. And it is as simple as reading length, jump and shapes. And if we failed to read it, then we immediately return in. Then we resize the shapes. And then... actually... Well, I don't know. Let's say that we use long as size t, probably. Or in 64T is even better. And everything will be longs. Okay, here we read the shape and we return in. Good. And here in this function, we try to read instance. And then we want to find the answer. Find answer, let's call it. Now we print it. And we return true. Okay, let's now write the function. Let's write the class answer. In our case, it's simply a long. Good. So the only thing left to do is to write find answer. Okay. Okay, nice. Very nice. So to do that, what is required here, I probably need to... First of all, we want to write the function. This function. We want to find all possible shape numbers. So let's write a function which finds shape number with some index. Shape number so find the area of the shape with this side and with this shape, with this number of angles. So this should be very easy. Yeah. It should be very easy because I think it is just always n times s minus 2 n minus s minus 3 over 2. That's what I think. Yeah, for example, if it is a triangle number, we get n times n minus... No. No. It should be... it should be 4. So, like this. Yeah. Or... n minus 1 plus 2. Even better. So when s equals 3, it is simply n times n plus 1 over 2. When s equals 4, it is n squared over 2n squared over 2, and so on. So probably this is the correct function. Okay, now how to solve the problem? So we want to find a cycle of a triangle number, square number, pentagonal number, hexagonal, heptagonal, and octagonal number. So some cycle of this form. We can always assume that it starts from the triangular number, for example, simply because in cycle there are all numbers, all sorts of numbers. We can start from any of them. And then we kind of want to go along it one by one. What do I mean by that? So basically each number is an edge. Basically each number is just an edge. Yeah, we have number, for example, we have triangular number 1, 2, 3, 4. I don't know if it's a triangular number, most probably not, but still, let's assume that it is. Now there is some square number 3, 4, 5, 6. A good way of looking at it is that we have an edge from what to what? From it is a little bit tricky. Can we just say that it is an edge from this number to this number? Hmm. No, I don't like it. I don't like it. Or do I like it? No, it's bad in terms of edges. It's bad in terms of edges. Well, I think what we can do is just some recursive search. So let's start. So we just go along all triangle numbers, for example, and start some recursion. What does the recursion do? It says, I have some starting number n. Then I try all numbers. Yeah, so for example, this number is 1, 2, 3, 4. So we try all numbers which start from 3, 4, and which are, for example, square numbers. Then we try going along them. And so on. So what does our recursion do? We need some current state. We need some current state. So what is a current state? So current state is some number of shapes which we still haven't covered. And there's nothing better to cover them than an unordered set. Let's call it required shapes. The next thing that we need to have is the starting number. So it's very important to have the starting number. Next, we want to have visited numbers. So we don't want to visit any numbers that are already visited. Right? What does it say about visiting the same number several times? Ordered set of 3 4-digit numbers. So basically an array. But they don't say multiset. Well, they say that each polygonal type is represented by a different number in the set. They don't say anything about visiting the same number several times. Maybe we can just ignore it and say that we can assume that we do anything we want with that. For example, we can say that we can do anything we want with that. For example, the numbers can repeat. So if that is the case, we can skip this problem. Let's just say that the numbers can repeat. It's fine. Then we only need to know the start, required shapes, and the current number. That is what we need. Well, I think that's good. So let's go. Let's go with that. So we say state. Well, let me think. Also, what do we do with the leading zeros? I think that the leading zeros should be forbidden if we want to forbid them. Okay, so therefore, let's do some preparation. Namely, I think we want to prepare the vectors. I think we want to prepare the vectors. So first of all, we want to prepare our step. So this number, we want to prepare to jump. I mean jump. Okay. And then we want to prepare numbers of all shapes that we are interested in. So basically, I think that is best represented by an ordered map from long to vector long. And for each element of this set, we will have a vector. So let's go. For why size t? We always use longs, not size t's. So for long n from 1 plus n, we say that long m equals shape number n shape, and if m is greater or equal than p10 of instance dot length, then break. But if m is less than p10, if m is at least p10 of instance dot length minus 1, then we put it in the shaped. So we say shaped mth dot push back m. Then it should be nth. It should be shaped shape. To speed this up a very little bit, we will start by saying list equals shaped shape. Therefore, here we just push it into the list. Okay, it's a very tiny speed up. And now we want to write some recursion. Well, actually, in our state, I also want to have all numbers, not only starting and current. And in order to do that, let's have a vector of longs. So, I don't know how to call it. Let's call it L. Okay, so we will start with 3. So for long, not with 3, but with the first required thing. So how to do that? So let's say that if instance shapes dot empty, we return 0, and otherwise we go starting shape equals instance shapes begin, oh yes, front, and also an ordered set of longs remaining shapes. Ah, no, I want to have state. I want to have state. And its remaining shapes, required shapes, it will be equal to an ordered set of long, which is composed from instance shapes begin +1 and instance shapes end. Good. And finally for state.l.front from the list, which will be called shaped starting shape. Yeah. What? What do you want from me? Okay, long x from this, and probably then I go like this. Well, it's fine. And then I want to write a recursion. So I go like vector states, vector long answer equals find chain of. It should be a vector. Yeah, find chain of state, and if answer is not empty, then we want to return its sum. And here we return -1 because no answer exists. Now we only need to write find chain, and that's it. It's not numeric? Wait, what? Ah, so again should be a constructor of answer. Okay, find chain needs a state and probably require shaped. The shaped array. Okay, let's go. So we need find chain of state and of this thing called shaped. So what is the idea? We have already some chain. For example, we have already chain of a triangular number and a pentagonal number and a heptagonal number. Then we need to complement it with 6, 4, 8. Yeah. So we will have required shapes equal to 6, 4, 8. So we will iterate over the next shape, which we will try to choose, and over all numbers in shaped S. So if S is from this set, we will try all numbers from this set, and we will try to continue this number with this number. In order for that to come true, we need these digits to coincide with these digits. We will do that with some iterator magic. It's not very hard. And after we've done it, we will continue our recursion. So either this recursion returns some answer, and we will propagate it down, or it will not find any answer. And the special case is when... What is the special case? So the special case is when our required shapes is empty. In this case, we have our first number and our last number, and we simply need to check that some beginning digits of this number coincide with some last digit of this number. And that's it. And the number of these digits is probably something like length minus jump. So we just need to find if these many digits here coincide with these many digits here. Very easy. And also, yeah, no, that's it. That's really it. Okay, let's do it. So as I said, let's first of all check out the case when I also want instance probably. Because I want to know the vector L. This is important. No, not L. What do I need? Wait, what is the vector L? No. Instance. Instance. Yeah, I want... Actually, what I really want is this P10. I want it so much that probably I'd like to make this lambda. Let's do it in lambda way. It will be slower, but in some way more lovely. Okay, why it will be more lovely? Because we don't need these trash arguments. Everything that we need is state. So let's call it autumn function find chain equals capture everything of state and returns long. We cannot unfortunately do this, even though we can include functional. It will still not work because it doesn't know which exactly type of function we are expecting here. In order for this to work, we have to write exact function type, but fortunately we know how to write function types. It's firstly the return type, and then in parentheses we write the argument types. Good. So now we know what a function is. And here we need to define this function. If we define it, we can simply call this thing. Okay, so first things first, if... No, why do you do it? So first thing first, if state dot required shapes is empty, that means some serious troubles. That means that we only need to check if the last and the first entries are compatible. So again, what does it mean to be compatible? If we have some number and some next number, this length is called jump. This length is called jumped. So we want these digits, length minus jump, coincide with these digits. So let's compare them. So this is the last thing. This is the last thing. So this is state.l.back percent p10 of instance.length minus instance.jump. This is it. Okay, and it should coincide with these digits, which can be acquired by dividing this by jump. So it should be equal to state L front divided by P10 of jump. So if these two numbers are equal, we can return something non-empty. Basically, we can return state.l. Otherwise, we return nothing. So, with that out of the way, we have resolved the case when state required shapes is empty. So now it is not empty. So let's iterate. I don't even know how to do that most properly. I don't like it. I think we need to copy it. We can do it even here, basically. Yeah, we can do it even here, basically. So we go through all the shapes. So we will try to remove it from this set and then return it back. In between these things, we will try to go through all numbers, but not so easy because we want to optimize it a little bit. And to optimize it, when we have a number, for example, this is a triangular number, we will not iterate over all square numbers. We will only iterate over such numbers that their starting part coincides with this ending part. So how to do that? We will take state L back percent this, multiply it by P10 instance jump. And let's call it long begin. Also, let's call long end begin plus this. I don't like actually the naming, so let's make it lowercase. What is that? So let's make it lowercase. So when we've done that, let's also say that we have const vector longs sizes equals shaped shape ampersand. And then we want only to iterate between these two numbers. So how to do that? Probably we need to prepare iterators. Like this and like this. Good. Now we just iterate between these two iterators. And between these two iterators, we try to propagate. So how do we do it? We go state dot l dot state dot l dot what dot pushback it, and we want to go on. So we do this, and if then we always have to state l in pop back it. Pop back. We always do it. We have to do it. But then if answer empty, we continue. And if it is not empty, then we want to return it. But we only want to return it if we don't want to break anything. So we need to firstly do this. Okay, this. Why do we do it actually? Yeah, we found an answer. Why do we do it? Actually, I'm not sure we need to do it. Yeah, because if we don't do it, we break it. But we only break it in the case that we found the answer. But for example, if we want to find all answers and not only one answer, then it will not be a good idea to just iterate. So we will have to do something like state dot required shapes equals this basically. Redo this assignment. Sorry. But we don't do it because already did it. Okay. Okay, let's try and see what it does for us. And we have, first of all, we have our test with length 4, jump 2, and three shapes of 3, 4, 5. And we have a test case of 4, 2, and 6, and 6 shapes of 3, 4, 5, 6, 7, 8. Great. Let's check that it finds something. Okay, it failed. So we would like to see where it failed. Now this time it didn't fail. And it even produced some output, didn't it? Maybe it produced some output, but we can't see it. Oh, here it is. No. Let's see what it does. txts / output problem.txt. I think it didn't open the file. For some reason, I think it didn't open the file. It says that it is in x64 debug. Probably we want to go into this folder. Want to go into this folder, into this folder, into this folder, into this folder, and only then in txts. So basically it is dot dot slash dot dot slash dot dot slash, and also here dot dot slash dot dot slash dot dot slash. Well, this time I'm more optimistic about that. Yeah, it did something and it failed, but at least it read the input for what we know. Okay, now we don't like what it is doing, but at least it's doing something. So our state is required shapes 4 and 5, starting with number 1035. Yeah, it already failed this case. Let's go inside. Oh no, it's so bad. So long shape from shapes. We remove it from the shapes. What the hell? Ah. Stop, there are no triangular numbers between these two values? What? What is IT begin and why is it an int? Vector constant iterator? Ah, you mean that 3600 is a triangular number? But is it? Ah, yeah, yes it is. And basically it doesn't fit us. So we insert this shape back. Then we try the next shape, which is the fifth shape. Required shapes, we erase 5 this time. Now it only consists of 4. Again, we compose these two numbers. Yeah, and we push back 3577. Then we go inside this new function. And again, we try to go inside. Yes, great. And this is a new problem now. Ah, it doesn't return anything. I see. We have to return empty set if we didn't find anything. Okay, this time it should work. It definitely should work. Yeah, you see, it's fine. It's fine this time. 2006 US? How is it possible? Why does it write 2006 US? What? 2006 US? 2006 US. How did it write 2006 US? But it is smaller than millisecond. 2006 US is greater than millisecond. What? What did happen? What happened, I mean? What? 2000? It's 10 million nanoseconds, not 1 million nanosecond. What? Ah, genius bug. It's so stupid that I did it. Okay, it happens. But it won't happen again. Okay, and in the release, we have even faster, I guess. Not really faster, but a little bit faster, maybe. Okay, let's see what it has in the output. So is it correct answer, basically? Yeah, so we need to sum up these three numbers, which we had here, which were 8128 plus 2882 plus 8281. Yes, it is correct. So we just need to print this answer. Yeah, great work. We're 29,000th, which is decent. So let's proceed with the next problem. cubic permutations. So the cube, this large number, is the cube of number 345. And it can be permuted to produce two other cubes. In fact, this is the smallest cube, which has exactly 3 permutations of its digits, which are also cube. Find the smallest cube for which exactly 5 permutations of its digits are cube. Well, there is only one way to do it. And it's write a program. Okay, for this new program, I would probably like to So the thing I hope for is that it doesn't overflow. But I think that this won't. This shouldn't overflow. But just in case, maybe we would like to have long arithmetics, arbitrary precision arithmetics. Probably it would be a nice thing. Probably yes. Probably we'd like to have it. Probably would like to have it. But I was strong enough to add arbitrary precision arithmetic. So our suffering will not come unused. We already did a lot, basically. So all this code isn't useless. We will have it. But the thing is, I want to have here MPZ class so that I can work with arbitrary precision arithmetic. Instance will be just long what? Long repeat. Yeah, that's what I want. That's what I want. So to read instance, we just need to return in greater instance dot repeat. That's it. It's very short. The answer is also very easy. I would probably call it C, but doesn't matter. We don't need any shape numbers. No state. We just need answer. Basically, we just need only this. Yeah. So the problem is that if we include gmpxx.h, it isn't available. That's a problem. It is not available, unfortunately. Well, what can we do with that? Probably it's something about CMake settings here. Probably it's something about it. Oh my god. Well, I don't remember what to do there. I really don't remember what to do there. Well, let's try to remember. So let's create some terminal window. Do I have a terminal window? Yeah, I have a terminal window. Can I make it bigger for you guys? No. I really cannot make it bigger. So this will be a small terminal window. I remember that I have C miscellaneous vcpkg slash vcpkg.exe. So then I can try to install gmp x64 Windows. Ah, you see, this is what we need. So it says that we need to find package pkgconfig required. Can I copy something? No? How to copy? Does right click just copies some string? Yes, it does. So we need to add this here. We need to add this here, and we need to target link libraries for this problem. Good. 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 You see, now it works. Probably. Fine, done should return something. Okay, this makes sense. This always definitely makes sense. Let's return 0. Okay, our input will be our input will be 3 numbers. One number. Our input will be one number, which is just the number of times this number is a cube. I think we can do it like this. Okay, so how do we do it? Well, let's do it the easier way. Let's do it the easier way. So, first thing first, how to detect two numbers with the same set of digits, which are permutations of each other. I think I will just sort them. So if I sort this string, it becomes 0, 1, 2, 3, 4, 5, 6, 6. Yeah, so I will want to have some sort of unordered map from string to long. And it says how many times this string was a sorted string of some digits of some number. To speed this up, I can replace this string with its hash, but for now it doesn't matter. Let's just have this string as this string. Maybe if we want to speed up this, we will save several times of complexity. So if the answer has length like 10, then we can speed it 10 times probably. But not sure. Not so sure that we need it. So it will just store how many times this string was the answer. Well, a little bit. So if instance is at most 0, then we can return -1 because no number no such number exists. Well, otherwise, we will go something like 2 pointers. So, for example, assume that we didn't find any numbers of length 4. So we have traversed over all cubes between these two numbers. We found no repeats, exactly 3 repeats. So we will have 2 pointers. Yeah, it's like 10 cubed. So we have pointer 10. And another one pointer is so what is the cubic root of this number? I don't know. We can see this. Where is C? Ah, yeah. Yeah, it is 21. 22. Yeah, so we have some number like 22. Okay, now then we start going through all numbers until we get something like this number. Again, let's calculate it. 47. So all numbers from 22 to 47 are stored. All 25 of them. We have stored them. And we know how many times each one of them is achieved. When we have exceeded this number of digits, we go again with the second pointer along these numbers, and we check each of them if it is done. So this is our plan. So let's do that. We have a left pointer, which is 1, and right pointer, which is 1. So for plus plus right. So what do we do? I think we can write like this. Good. I don't want to have any extra includes, so we need to remove functional, remove algorithm, remove numeric, remove set. That's it. An ordered map from string to long. Okay, so if right size is greater than also I want current size. It is also 1. Yeah. So if let's first of all prepare string. String right str equals right dot to get string. Okay, we have constructed the string. So if this right string is greater than size, then we will have to do something, and in the end size will become equal to right str.size. After that, we will say that occurrences, we will sort it, right str.sort Okay, we will sort it. And say that we do plus plus occurrences of right straw. Great. So what do we do here? You can't compare. What's wrong with you? What? You can't cast. Can we do it like this? Still no. How can you construct it? Unsigned long, but not unsigned long long? Are you crazy? Are you crazy? What the hell? They are nuts. They're really nuts. So I have to say two string from this as size. This is so dumb. This is really dumb. I can't even begin to explain how dumb it is. I can't turn long long into capital long. Bad. Okay. Never mind. So when we've done it, we want to go along all numbers left. So while left is less than right, so if occurrences of left we create left string equals left to string, then we sort it and if occurrences of left str equals instance dot repeat, then we return left. Otherwise we don't return left and we just go plus plus left. Okay, and at some moment it just works. Okay, I hope it's fine. Yeah, and you see it worked. So it says 112. Wait, what? For some reason I cannot believe it. Ah, because I never write cubes. What the hell am I doing? We also need to write some function. Return n times n times n. Or Power? Do you have power? Like, do you have power? No? Wait, what? How to find powers? Well, I will need to learn that because I don't know. Okay, for now we can just multiply it 3 times by itself. Good. Okay, so here we want to let's also say fstr, which is basically f of n dot get string. And we always use fstr instead of get string. That's what we need to do. And in case of the left ones, we also do it. Okay, now it should be better. Yeah, you see, it's much better. And it finds something. I even hope it can find some greater answers. Right? Ah, you see, it's slower and slower. Wow, I like it. We see some pattern here. It has mass. Wow. I like it. So let's return our cubes and get finished with this problem. So we need to return fstr. Ah, f of it. F of left. It's really fun. Okay, so we just copy this number and paste it here. Nice. Okay, the next problem is 63. Powerful digit counts. The 5-digit number 1687 is a 7 to the 5th power, which is also a 5th power. Similarly, the 9-digit number, this is a 9th power. How many n-digit positive integers exist, which are also an nth power? Oh, that's fun. It says that it is a finite number. So there are finite numbers. So why should they think so? Well, if we take 10 to the power n, it is already n plus 1 digit. And if we take 9 to the power n, it is, well, it's some number of digits. At most n, but sometimes, so at some moment it will become less than 10 to the power n minus 1. And at the exact moment when it happens, 9 to power n plus m will always be less than 10 to the power n plus m minus 1. Simply because it is multiplied by a smaller number than this one. So we need to stop at the exact moment when this becomes less than this one. And before that, we can just do it with a calculation. Which we will do. I think we can also do it with GMP. It's a nice thing, which I like having around. We will need strings, we will need... I think we will need powers, because it's really strange that we didn't have powers. Well, do we have, like, function power? I really don't know. What? Well, I actually know somewhat optimal way to do it. So in... Not somewhat optimal, I don't know how to put it, but... It is faster than O of uns, I mean, times the arithmetic. So if the arithmetic was a constant time, then it's easy to find the answer in O of uns time, but I can do better. It is basically the observation that if you have a convex body, you can find its area not by calculating all points, but by going around its boundary. And if you go around its boundary, then you can just add up all lengths of such segments and find the area of this figure like this. What do I mean in terms of this problem? So assume that we have some squares. But basically, what I want to say is that instead of 9, you can have any digit here. You can have any digit here. You can have here 8, and it's also true that if 8 to the power n is less than 10 to the power n minus 1, then all next powers will also be less than it. For example, let's consider squares. Let's consider squares. So all squares... Sorry. Actually, I know what I want to have as an input here. I want to have number 10 as an input. So this will not be an inputless problem. So first of all, first powers. So first powers, which are also first one-digit numbers, are from 1 through 9. Okay, but somehow, if we now take two-digit numbers, then we are only interested in numbers starting with 4, because here we have 16, 25, etc., 81. And if we start with 3, then 125, and so on. So all numbers from this to this, they are always same number of digits. And if this becomes smaller number of digits, then we can go on. So this will be some sort of such shape, and we just go along its left boundary until it vanishes, instead of going through all numbers. Going through all numbers does not help a lot. So to wrap it up, let's write a function for powers, because apparently I don't know how to write it without the function. I really don't know, yeah? Power. Power. Do we have powers? Do we have powers? Maybe integer power? Very strange. Maybe I can go inside this file? No. I need to first update this file. And now I can go inside this file, right? It already has all of this. Okay, can I find here power? No, nothing about powers here. Maybe I don't know what to say. You really don't have powers. Okay, let's do it. So, okay, while... Okay, long ons equals 1, while b, if b and 1 ons times equals a, if b less equals 1, a times equals a, return ons. What's wrong with you? B, let's compare it with 0. Okay. And instance will be base. It will be just base. So here we write. Here we write. Here we write. So long a equals 1. For long... okay, we have long ons equals 0. For long left equals 1 and power equals 1. L okay. Okay, we can just make it an infinite cycle plus plus n. Now we go while power L to the power n dot get str dot size is less than instance dot less than n, basically. What the fuck? Okay, let's hope that it is just... Let's just do this, but it is crazy that I cannot get a normal integer. So while this is true, I plus plus L. And also I only do it while L is less than instance dot base. Okay, at some moment it stops doing this and I add it to the answer. And we return answer. Good. That's it. That's the problem. Okay, we're probably interested again in all sorts of bases from 2 to 16 probably. Let's see what it pleases us with. doesn't really want to stop. Even for binary. Even for binary, it doesn't want to stop. Ah. Okay, let's just do it like this. We will help ourselves a lot by just doing this. Okay, for 10 it's really doing... Ah! No, 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 no. It's really bad. And stupid, because... No, we don't want to get through here. We don't want it. We want to take care of 2 powers of 10. The current power of 10 and the previous power of 10. Right? So now gets through. We're interested in. So we're interested in the fact that this number is less than the previous power of 10. So let's also have p equals 1. And here p times equals 10. And here we want to compare it with p. That's what we want. Why does it die? Wait, what? Why does it die? Why does it die exactly at 10? Ah, I'm again an idiot. Base. So now it should die at 2, if I understand it correctly. Wait, what? What? Ah, it dies at 11, of course. It dies at 11. Yeah. Understood. Okay, let's see the answer. It says that there are 49 such numbers. Well, it's interesting. It's definitely interesting. 49. Good. 64th problem. So all square roots are periodic when written as continued fraction and can be written in this form. Yes, it is very well known. Well, any irrational number can be written in this form in unique way if all these ai's, a0 is just an integer and all ai's are positive integers. In this case, there is a unique way to write any irrational number as an infinite continued fraction. And for rational numbers, there are exactly 2 ways to write them as a continued fraction. One of them ends with 1, and the other one does not end with 1. Well, one of them ends with 1 and has at least 2 terms, and another one exactly one term less long, exactly one term shorter, and either it does not end with 1 or it's only a0. Yes, this is all of this is true. Yes, there is such thing. It will be repeating for any quadratic irrationality. If we call quadratic irrationality any number of form square root of a plus b over c, then such and only such numbers will be periodic continued fractions, where a, b, and c are some integers, where a is positive integer, which is not a perfect square. Exactly 4 continued fractions for n is at most 13 have an odd period. How many continued fractions for n at most 10,000 have an odd period? Ah, okay. And we're only interested in irrational square roots. Probably let's, as an input, take 1 and 2. What I mean by that is we have 1, which is the residue, and 2, which is the modulus of the period. Okay, so we want to as the input we want to have like 13 1 2 and 10,000 1 2. This is our inputs, and we're interested in the continued fractions. So I don't think we will have to use algorithm and string, but we will only need vector or something like that, or not, or we would like an ordered set. Yeah, we would like an ordered map. Yeah, we would like an ordered map. Okay. So this is an interesting problem. I'd like to solve it. Powers will not be applicable here. So our answer will be long, and our instance will be residue, modulus, and upper bound n. Okay. Okay, how to find this answer? We will basically just initiate answer. And then we will return it, and inside this function we will go through from 2 up to instance dot n. We will find the period, and we will check if period percent instance dot modulus equals instance dot residue. If that's the case, we plus answer dot count. Let's call it count. It's funny to call it count. And we return answer. Now let's find the period. How to do that? Well, For some reason, it always looks like it's starting from this first number. I don't remember such a fact about periodic fractions. Well, let's assume that the first number can be included in the period. It can be. It can happen. Well, in that case, so we store our irrationality in this way. So we store it in a way n times a plus b over c. So we store numbers a, b, and c such that our current number has this form. In the beginning, we can say that we have a triple 1, 0, 1, because we have just square root of n times 1 plus 0 over 1. Okay, now we want to perform two primitives. So the first primitive is to get the truncate the number. I mean, not truncate. Take the integer part. Just a moment. So how to get the integer part? Well, let's now take the... Okay, I will just say what we want to do, and we will understand which primitives we need. So we have some irrationality. We want to write it in this form. Well, unfortunately, we need to start with this number. I don't know about unfortunately, but we need to start with this number. If we don't know a0, we will not figure out the rest of the numbers. So a0 is actually just floor of IRR. So they are basically equal. If we find it, then the rest of the things is easier, because this now is IRR minus a0, and then we invert it. Invert it. When we invert it, this number is 1 over IRR minus a0. Let's call this number R0. Let's call this number R1. Let's call this number R2, etc. So what we want to do is these operations. So first of all, we say that IRR equals R0 equals IRR. Oh, sorry, what I did? R0 is defined as IRR, and then AI is defined as floor of Ri, and Ri plus 1 is defined as 1 over Ri minus AI. So this is what we want to do. We want to define these two operations. Great. Great. I'd like to say that we also want the third operation, which is find out that it is infinity. Or otherwise compare number with 0. This is what we want to do. Is it true that Ri is 0? Not Ri, but Ri minus AI. Is it 0? We want to find out. So let's do it. I think we need to first start with this one because it should be easier. So let's assume that we have some numbers. Or I don't know, let's call it kmn maybe. So we have k square root of, no, n is already under the root, so okay, let's call it abc. I don't know, I don't like a because a is already used. Okay, let's call it bcd. So we have b square root of n plus c over d. Also we want to subtract integers. So if we want to subtract ai, it becomes b square root of n plus c minus d ai over d. So this is easy. Subtracting integers is easy. What about dividing 1 over b square root of n plus c over d? So this is basically d divided by b square root of n plus c. And the standard way of doing it is multiply both numbers, denominator and numerator, both by the conjugate. The conjugate of such number is defined as c minus b square root of n. So if we do that, we get this. Great. Now we can easily find out that we have minus bd times square root of n plus cd. And we divide all of that by c squared minus b squared n. Probably after that we would like to divide this, reduce this fraction by dividing by GCD. Is it true that now GCD is equal to 1 if it was equal to 1? I'm not sure about that. Of course, if there is a prime, a common prime in B, C, and D, then it is also present in all of these numbers. Not only present, but also in double multiplicity. However, not visible at all. However, maybe it can spawn even if it wasn't present. And of course it can. Maybe we can even see it here, right? Maybe we see it here, right? For example, in this case, we reduce this fraction by 7. So probably we want to reduce the fraction after this operation. And we will do it. Okay, great. And final thing is to find the floor of this number. So we want to we have such a fraction. We want to find maximum m such that this fraction is greater than 0. This is what we want to do. Oh my god. How can we do that? Well, the first idea that I see here is that we want to find maximum k. So we want to find basically b square root of n plus c, and then divide it by d and take again floor. So this is the first idea. Because this operation divided by d some integer is very easy, and actually adding c is also very easy. Because we just add c to the integer. So now, and also b can be put into the square root. So now the basic operation is find bn squared floor of such a number. How to find floor of such a number? Well, I don't know. It depends on what we have in our beautiful library. So does NPC allows for doing it? And also, what about finding the period? Basically, we store all these numbers R0, R1, R2, etc. in some unordered map. So, for example, for this number R0, we store unordered map R0 equals 0. For this number, we store 1, etc. And if at some moment we find number Rj, which is equal to Ri, then in our unordered map, we will see j and I, that they repeated. So the difference between these two numbers will be put as the answer. So to do that, let's say that we have, I don't know, no, we really need the operation of square root. Let's find out how it can be done, I think. So GMP square root. Can we do it? GMP squared t. GMP xx squared t. Can it help us with this? GMPZ sqrt. MPZ class. Calculate square root and the remainder. What? Okay. Probably. So there is some strange function for this. For long I equals 0, B equals 1, C equals 0, D equals 1, infinitely plus plus I. Okay, so first of all, what? So first of all, we want to find the square root of bn squared. No, not bn squared, but b squared n. B squared n. So we take b times n and find the square root of this number. Actually, is there an ordered map from long? So I don't know if it is hashable. It will not be known until we recreate the CMake lists. No, it does not exist. What? STD. Wow, it exists? Doesn't it? It exists? What? It exists. Base is not the part of instance. Of course. Hash of long does not exist. Okay. Okay, BCD. So first of all, we want to find the floor we cannot what? We cannot define two elements of different types? Seriously? Okay. Sad, but fine. Okay, so long I is 0 plus I. So let's define its toString. Return this plus b get str plus this plus c get str plus this plus d get str. Nice. So we want to find the floor of I or R. Let's define integer square root. Okay, first of all, if n is at most one, then return n. Next. What do we do next? And next we want to ask ourselves if it exists in U. So auto it equals u dot find. Let's also calculate n str equals n dot get string, and if it finds, we return 80 second. So this is our actually memoized square root. So otherwise we have to take this strange function from GMP. Let's steal it, and it says that we need to what? We prepare these two numbers. Okay, let's also return pair of long and int, long and bool. And bool says whether or not. Let's return remainder here. Good. Root remainder, and here we put n. And we simply return, and we say that unstr equals root rem, and we return root rem. Good. So this is I square root. So how do we do it here? We start with root and rem equals I sqrt of b times b times. Actually, I think that this exact map u can be static. This makes giant sense. Okay, we can avoid it that, but I don't know. We cannot avoid that. Okay, let it be not static. It doesn't matter. I will add that it can be added static. So we found square root. And then if rem is 0, then this is an exact square root, and in real quadratic rationalities there cannot be exact square roots. They never happen. They never happen at all. That just means that n is a perfect square, because b is non-zero always. If things are such, we have to say that remainder is, we just return. Not return, but break. Okay, now remainder is not 0. Then we found the root. Then we need to subtract c and divide by d. And also, let's assume that we know that this number is positive. Yeah, I think we can agree to know that this number is positive. So basically, from root we subtract, we add c, and we divide it by d. Yeah, we add c and divide by d. So we get something here. This is basically a. We found a. Now when we find a, what the hell is that? Now when we have found a, when we have found a, we want to subtract it from IRR. So to do that, we say IRR dot B dot C minus equals A times IRR dot D. So we did this. And then we want to invert it. So to invert a fraction, we need to replace B, C, and D with these values. So minus BD, CD, and some strange thing. Minus. Okay, I'm. Minus BD. CD. And the final one is crazy. It's C squared minus B squared N. Okay, we constructed a new one and we want to reduce it. Let's call just the reduce function, which we will write later. Okay, how to reduce? Long G equals. Do we have GCD? Yeah, we actually have GCD. What the hell? Define binary function from this. What? Can I write like this? No. So, and I want to take absolute value. Okay. So GCD is used. Can I have absolute value? Are you sure that it is? STD ups? It doesn't know what it is. Also, I always want D to be positive. So after the reduction, we want D to become positive. Okay, let's just do it this way. And if D is less than... D is already positive. Let's say that D is already positive. So if G is up of G, can I write like this? This time I can. What? So I can write like this, but I cannot write like this? I can this time. Something happened. Something that I don't understand happened. Maybe it was like this. And then it doesn't work. Okay, maybe I just messed up a little bit. Okay, probably that's it. Probably that's it. 64 here. No, it does not want to work so well. It doesn't work to work. It doesn't want to work so well. Because I just infinitely long. Yeah, I just drew a very long computation for some reason. So what I really need to do is to say that ort it equals u dot find IRR dot str. Not u. I need. Okay, let's call it ISQRT cache. And let's call it here the same thing. IRR cache. So here, so if it is not IR cache dot end, we define period as I minus it second and break. Otherwise, we just calculate everything that is relevant, reduce, and we call it a day. So we say that IRR cache of... No, we don't do it. We do it here. IRR cache of IRR str equals I. Well, that's something nice. But this is slow. Because I'm in debug. In debug it shouldn't be fast, but I think in release at least it will be faster. Yeah, faster than second, although already takes time. It takes time. So what does it say? It says 1322. Well, so it already took a lot of time, so I think for now we will take a pause. Great. Thank you for watching.